In the last lecture, we developed a formulation for a 2D rectangular element. In this lecture, I'm going to show you how that same formulation can be used for a more general quadrilateral element where the sides may not be all parallel or all the same length. And then explain how we can use something called isoparametric formulation to map that general quadrilateral element to a standard square element. I've placed up here a diagram of a general quadrilateral element, and I've also placed up here the final formulation that we found at the end of the last lecture for our 2D rectangular element. This same formulation can be used for the general quadrilateral element. I'd like to draw your attention to the stiffness matrix, which is formed by the triple integral on the left-hand side of the equation. This is the triple integral that, when all is said and done, will, for a general quadrilateral element or a rectangular element, will be an 8x8 matrix that gets multiplied by our displacement vector I've been calling U. I briefly mentioned at the end of the last lecture that this triple integral, which forms our stiffness matrix, that the integrand, which is formed by the B matrices, or the B matrix and the transfer of the B matrix multiplied by the D matrix, that these B matrices for the rectangular and therefore the quadrilateral element are still dependent on X and Y, which means you have to leave them inside this triple integral. Also, remember that you're not really solving for one quadrilateral element. This one quadrilateral element will exist inside a larger global mesh of rectangular or quadrilateral elements, which means that you need to derive a different B matrix for every single local element, and you need to integrate that over that element for every single element inside your global system. As you've seen from some of your lab work, for the types of problems that we're actually using computers for, there may be hundreds or thousands of local elements inside of your global mesh. Deriving the B matrix for every single quadrilateral element and then integrating over the product of these three matrices time and time again is rather difficult. It's also made more complex by the fact that every different element will have a different shape. While it's easy for human beings, or relatively easy for human beings, to adapt for different shapes, it's difficult to write a computer program in this formulation that will allow the computer to use a simple repetitive algorithm time and time again for all the various shapes that you might have a general quadrilateral element for. So what we're going to do is we're going to use the isoparametric formulation to what's called map this general quadrilateral shape into a standard square shape. So the main reason for developing the isoparametric formulation is, again, so we can write computer programs using a standard algorithm that will work for all of our general quadrilateral elements. This also will allow us to, the isoparametric formulation will also allow us to not just work with quadrilateral elements, but any element that has 4 vertices. It can even have a curved side or two, allowing us to form elements at our boundaries of more complex two-dimensional shapes. Indeed, it's the isoparametric formulation that's used in most of the commercial FEA software that's currently available. Finally, by using the isoparametric formulation, we set ourselves up to more easily and more readily use the types of numerical integration methods we'll be learning in a future lecture, so we don't have to solve these integrals, not just this integral, but all of the integrals, analytically, we can use numerical integration techniques, and by using the isoparametric formulation, we're setting ourselves up to using those techniques more readily. So how are we going to go about doing this? I'm leaving up here our general or an example of a generic quadrilateral element, and I've replaced my total formulation for the rectangular element, and I've just placed up here our formula for the K stiffness matrix. I've simplified it a little bit. We're in two-dimensional space. We're modeling our three-dimensional element as a two-dimensional element. So that triple volume integral I can think of as an area integral, integrating over the area of our quadrilateral element and then multiplying it by a constant thickness. But this still means that I need to integrate over my area of my quadrilateral element. As you can imagine, the area of this quadrilateral element is a little bit difficult to define in terms of x and y, so we can integrate this in terms, replace this dA with a dx, dy, and come up with appropriate bounds for our integration. What we're going to do is we're going to take our real axes, x and y, that exist in actual physical space, and what we're going to do is map them to, you might say, I don't want to say imaginary, but virtual coordinates s and t. What we're going to do is called a mapping. What we're going to say is that for every xy point that exists in my xy plane, for every unique xy point, there is a unique point in st space. That is to say that for any location inside this quadrilateral, I can write that a location in x space is a function of my location in st space. So x is a function of s and t, and likewise y is a function of s and t. This mapping works both ways. So if I have a unique point in my xy space, it exists in a unique point in st space, and any unique point in st space can be mapped back to a unique point in xy space. It will turn out that our stiffness matrix K, which we wrote like this in xy space, we can also come up with the same K matrix using a similar formulation in st space. So I can get the same K matrix, but now instead of integrating over dx and dy and having to figure out what my bounds of integration are in terms of x and y, I'm now on a standard square. My bounds of integration are going from -1 to 1. My B matrix, D matrix, and B matrix that are over here are also over here. The B matrix will take on a slightly different form, and we'll discuss that in a future video. The only thing different is that now, instead of a generic dA, I'm now integrating over ds dt. I've also introduced a new matrix you haven't seen before, the so-called J matrix. Actually, the J matrix is what's called the Jacobian. And I'll explain more about the Jacobian in a future video. In this location where I have the Jacobian, I have two lines on either end of the Jacobian. What that means is I'm talking about the determinant of the Jacobian. And again, we will discuss that in a future video. All right. In our next video, we will learn how to do this mapping from xy space to st space. And in doing so, we will find how to formulate the shape functions for our now regular square element. Before we go to that next video, I'd like to point out that while we're discussing the isoparametric formulation in this lecture, and the goal of the isoparametric formulation is so that we can write standardized computer algorithms, we're not going to go that far in this lecture. We're near the end of the course. This is lecture is designed to introduce you to some of the concepts for isoparametric formulation. You won't be ready by the end of one lecture in isoparametric formulation to write computer programs that utilize isoparametric formulation. This lecture is just to introduce you to some of the concepts. I'll see you in the next video.